So today we're going to study about gases. So a gas is a substance or matter in a state in which it will expand freely to fill the whole of a container, having no fixed shape like a solid and no fixed volume like a liquid. And a more chemical one would be that it's a phase of a matter in which particles are very far apart one from another, move more quickly and aren't attracted to one another. Because these molecules in a gas, they are so far apart one from each other. Gases are much less dense than liquids or solids. Okay, so if we had a container, let's say it's a box. This is totally not a box, but okay. If it's a box, we would have on the solid, it would have a shape, for example, a loaf of bread. So it has those lines. Okay. So this is a loaf of bread. It has a shape. If you don't touch it, it has a shape. So it has a shape. They are more tied together. Okay, they're very tight together, and it doesn't change, right? If we had a liquid, right, it would be different. Let's think in the water. It changes, right? If you move a cup of water, the water is going to like, ooh. So it changes its shape, but it does not change its volume unless you pour it on the table. But okay, it doesn't change its volume. And but the gas, they are not too far apart, but they are apart one from each other. And the gas, they'd be like very apart one from each other. So we know that the gravity between the two things, that attraction force, is m1 times m2 over r squared. So if they are apart, they're going to be apart squared. So this force is going to be way lower. So they don't have a particular shape nor a volume, right? Okay. And we know that gases, they are not like perfect. They sometimes behave in different ways. So the chemists and physicists, they created a gas called ideal gas, which is a very simple gas. It doesn't it doesn't have any inner um, how do you say that, reactions, no inner reactions, and it's very simple. And the IUPAC, which stands for it stands for interna International Union of Pure and Applied Chemistry. So that's the IUPAC. And this union, they set the standard. The standard temperature is 200 and oops, it's 273 Kelvin, and its pressure, it's 10 to the fifth. Oops, 10 to the fifth would be to the third, and to the second plus 10 to the fifth Pascal, which is Newton by meter squared. But this is a huge number. We could say that this is 10 to the 2, 10 squared, right? Kilopascals, okay? Kilopascal. And the gas temperature is measured in Kelvin, and Kelvin is same thing as Celsius, added 273. We know that Celsius is equal to 5/9, 5/9 times Fahrenheit minus 32. So Kelvin is 273 is equal to C plus 273. Therefore, it's 0. And from here, we can say that Fahrenheit is equal to multiply by 9 divided by 5 times C. Okay, 9/5 times C. And all of this, and then all of this, you sum 32 at 32. Okay, so we know that C is equal to 0, therefore Fahrenheit is equal to, all of this gives 0, 32 Fahrenheit. So 273 Kelvin, that's equal to 0 Celsius, which is equal to 32 Kelvin, 32 Fahrenheit. Okay, okay. And okay, 10 to the 2 kilopascals or 100 kilopascal. And we have a formula for this ideal gas. And this ideal gas, it behaves in this way. It has an initial pressure, an initial volume, and also an initial temperature. And if you multiply its pressure by its volume and divide by its temperature, it's going to be the final, equal to the final pressure times the final volume over the final temperature. So pressure, the SI unit for pressure is, well, force over area. Force is Newton, area is side by side, distance is meter, meter squared, that's equal to Pascal. Yeah, the SI unit is in Pascal. So it's going to be a pressure, which is Pascal, times volume, which is cubic meter, divided by temperature, which is Kelvin. So Pascal times meter, cubic meters divided by Kelvin. Okay. So let's do some exercises. A spray can is used until it is empty, except for the propellant gas. So until here, this propellant gas, and it doesn't matter. You just can say a spray can, which has this pressure of 1,344 torr. So torr is a pressure measurement. Okay, 1,344 torr. 1,344 torr. We're going to do this two ways. We're going to do it with the pressures and things that it gave us, and we're going to do this on the SI unit. Okay, so let's begin with the SI units. It's Pascal. To change from torr to Pascal, we need to multiply by 133.320.322. And I'm not going to do these on my head because it's going to be a little complicated. So we're going to 1,344 times 133. That's it. Oh, sorry. 3. Okay, this is in Pascal. Da, 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 da. So that is in Pascal. Let's just change this. This is the same thing as 1.7 times 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5. Okay, let's leave it like that. So at 23 degrees Celsius, we know that we're going to take this to Fahrenheit, to Kelvin, which with some 273 plus 2 is 296. 296 Kelvin. 273 plus 23. Yeah, 296 Kelvin. And okay, it says that it's thrown into the fire with 475 degrees Celsius. And we want to know the pressure, okay? So 475 actually, plus 273. So 3 plus 5 is 8. 7 plus 7 is 14, goes 1. 4 plus 2 is 6 plus 1 is 7. 748 Kelvin. Is this correct? It's 273 plus 475, 748 Kelvin, and I want to know the pressure, which is Pascal. If you pay enough attention, you know that PV over T is equal to PV over T, but it doesn't give us the volume. So one of two things. First, it wants to find out the volume, but we know that it does not want to find out the volume because it says, what will the pressure be? What will be the pressure in the hot can? So not that. Okay. And the second thing is that is isochoric, which means that the volume doesn't change. So constant, we don't need to write the constant, which is what actually happens. So P1 over Q1 is equal to P2 over T2. We want to find out P2. So P2 is going to be what? P2 is equal to multiply there T2 times P21 over T1. You see? Bam. And I changed here, right? P2 should actually be in this side, but it doesn't matter. Same thing. Okay, so now let's change. So we know that T2 is equal to 748 what? 748 Kelvin times P1, which is that thing. 1,700 and no, 179,784.768 what? Pascal divided by the temperature 1, which is 296 Kelvin. 296 Kelvin. You see, I've written the units for two reasons, because we know that the Kelvin will be canceled out. So yeah, pressure in Pascal, well, it makes sense. So yeah, it's right. And also you can see why they cut, why they cancel out. So Kelvin cancels out with Kelvin. And so we have to multiply this horrendous thing. Here. This, and then we'll multiply this by 748. 748. And now we divide by 296. And we get this. And so this is the same thing as 4 to the 5 times 10 to the 14. Okay, Pascal. But it actually didn't ask us this. It asked us on Tor. So we're going to do the same thing, but we're going to do, instead of with Pascal, we're going to do it with Kelvin, because we don't deal with nor C, which is Celsius, nor Fahrenheit. It's Kelvin. So it's the same thing. It's 748 times 1034 divided by 296. So if we do it, 748 times 1334 or 44. 44. Bam. And we divide by 296. Yeah, 3.39, which 3 dot. Okay, so it's 3.39696. That's 1, 2, 3. Okay, so it's 3.39, which is 4 times 10 to the third. With oops. And we get here, the answer is 3.40 times 10 to the 3 torr, because we know that it's pressure. It's pressure. Okay, very good, very good. What is the temperature of an 111.2 liter sample of carbon monoxide, CO, at 744 torr if it occupies 13.3 liters at 55 degrees and 744 torr? Okay. Let's see. I know that this, we know that PV over T 111, that's equal to PV over T 222. So it says, what is the temperature? The temperature, okay, of 100, okay, if I know that, pressure, 744 torr, times torr, okay, times volume, 13.3 liters over temperature, 55 degrees, but use some 273, gives 8, 12, 328. Is that correct? 55 plus 273. Wow, 328. This is Kelvin. Okay, I know that that must be equal to PVT. And what is pressure? Oh, pressure is 744, so it didn't change the pressure. 744 times volume, which is 11.2. liters. This is torr divided by our temperature, which is what we want to know. We could cancel out the 744 because it's the same thing. It's isobaric, but let's just let it there. So what we have to do, we multiply there, divide there. Okay, it's going to be 328K times 744 times 11.2 liters. This is torr. And this is Kelvin torr liter, okay. Bam. Divided by 744 torr times 13.3 liters. That's equal to temperature 2, right? Because I multiplied here, okay? Multiply there, so 744 torr times 11.2 liters multiplied by 328 Kelvin, okay? And then we divide 744 torr times 13.3 liters. Okay, so torr cancels out with torr, liter with liter, and we're left off with Kelvin. Temperature, Kelvin. Okay, good. So now 744 cancels out with 744, and we have the following. 328 times 11.2, right? And then we divide by 13.3. 276 Kelvin. 276.21 Kelvin. We're dealing with Kelvin. 276 Kelvin. Or in degrees, which we just have to take out 273, which is 3 degrees, but we are currently working with Kelvin. Okay, let's do one more. A 2.5 liter volume of hydrogen measured at negative 196 degrees is warmed to 100 degrees. Calculate the volume of the gas at the higher temperature, assuming no change in pressure. Okay. Same thing. PV over T, that's equal to PV. Oops. That's equal to PV over T. Okay. So there is no change at pressure. Therefore, bam, this out and this out. Okay, the pressure, the volume. I want to know the volume, 2. Okay. Want to know the volume, 2, 2, 1, 1. So I want to know the volume 2. Okay, volume 2, that's equal to T2 times initial volume divided by T1. Okay. What is the second? It's 100 degrees. If we sum 273, guess 373. Okay, 370. Ooh, I need more space. It's going to be okay. P2 pressure. No. T2. No. V2. That's equal to T2, which is 373 Kelvin times the initial volume, which is 250 liters, divided by negative 196. Negative 196 plus 273, which is the same thing as 273 minus 196, 77 Kelvin. Okay, so 373 times 250 divided by 77. 12 what? 12.1 liters. Oh, yo. K with K. That's why liters. Okay, let's see. 12.1 liters. A balloon inflated with 3 breaths of air has a volume of 1.7 liters. At the same temperature and pressure, what is the volume of the balloon? 5 more same-sized breaths of the balloon. If 5 more same-sized breaths are added to the balloon, what is the volume? Okay, will the volume change? Okay, volume PV over T, that's equal to PV over T 2, 2, 2, 1, 1, 1. Okay, so what does it say? A balloon inflated with 3 breaths of air has a volume of 1.7 liters. So volume 1.7 liters. 1.7 liters. At the same temperature and pressure, so pressure didn't change, nor did the temperature. The same temperature and pressure. What is the volume of the balloon with 5 more sized breaths? So let's see. The volume, that's equal to, let's say, that's equal to temperature divided by pressure, okay? Better. The volume, 1, is equal to P2, V2, T2, multiplied by T1 divided by P1. So the volume is going to be what? 1 breath. So 3 breaths, that's 1.7 liters. 5 breaths, that's going to be what? 5 breaths, that 1.7 liters, 1.7 liters, divided by 3 liters. Okay. 5 times 1.7 divided by 3. 2.8 liters. 2.8 liters. Oops. This one. 5 more. If I add 5 to what I already had, 4,533. Yep, that's it. 5 more. 4.5 liters. Okay, yeah.